So, good afternoon, all of you. So let me start. So yesterday or in my last class, I have explained that different type of generators which are used in the wind energy conversion system. So that I already explained this part. Okay, now today I'm going to explain this WFET induction generator based wind turbine system. So in WFET, why this is called WFET, or in some books you may get double output induction generator. So why this is our double output, that I already explained, because stator is also the power is delivered to the load or to the grid from the stator, and also from the rotor winding, but the rotor terminals or rotor windings are connected via the power electronics converter circuit. Okay, so if I compare this DFIG based or DFIG based wind turbine system with permanent magnet synchronous generator based wind turbine system, you just see here the power electronics devices. Here the power electronics devices are connected with the stator windings. Okay, so as the power electronics devices are connected with the stator windings, that's why the rating of the power electronics converters are more as compared to the DFIC. Why you see here the rating of the power electronics converter are less? Because the power electronics converters are connected with the rotor circuit. So these power electronics converters, they are handling only the sleep times of the stator power. Okay, they are handling only the sleep times of the stator power. Now, what is the value of the sleep for induction motors? The sleep is the range for the sleep is 0 to 1. Okay, but in DFIG, the sleep is considered from 0.1 to 0.3. So if I consider the sleep is equal to 0.2, and the stator power is 1 kilowatt. So 1 kilowatt into 0.2, that we will get 0.2 kilowatt only. So if I consider the stator power, this is equal to 1 kilowatt, and the sleep is equal to say 0.2, or you can consider 0.1, 0.3 also. So if I consider this, then you will see there is a relationship among rotor power, this is the rotor power PR, then sleep, and the stator power. So this is the stator power. Okay, so this is the relationship. So in this relationship, if we put these two values, then we will get PR is equal to 0.2 kilowatt. Okay, so this power, this rotor power, it will flow through the power electronics converters. Okay, that means this power, it will flow from the rotor winding to the grid or to the load via the power electronics converter. That means this much power only flow through the power electronics converters. Whereas if I consider this one, you just see if the stator power is 1 kilowatt, so this total power, it will flow through this one. Okay, that's why the rating of this is 1 kilowatt. We have to design the power electronics converters in such a way that they must handle 1 kilowatt. Okay, so definitely the rating of the power electronics converter will be more here, but here they have these two converters. These two converters, they will handle only 0.2 kilowatt. Okay, so if I compare this power with this power, then this power is very, very less as compared to this one. Okay, that's why the power electronics converters which are used in the DFIG based wind energy conversion system, that is the rating of those converters are less as compared to the power electronics converter which are used in the permanent magnet synchronous generator based wind energy conversion system. Okay. And you just see here, and also one more thing is there. What is the frequency of the frequency of the rotor power. The frequency of the rotor power is denoted by Fr. So there is a relationship between rotor frequency and the stator frequency. So this is the relationship between or we can say the among rotor frequency, slip, and the stator frequency. Now, if the stator frequency is say 50 hertz, okay, stator frequency is 50 hertz, and the slip is 0.2. So if we substitute these two values here, then what we will get? We will get 0.2 into 50. That means 10 hertz. Okay, so this is the frequency of the this rotor power. So this frequency, as the frequency of this power is 10 hertz, then this power we cannot use directly, because whatever the, if the grid is connected, then the grid frequency is 50 hertz. If the load is connected, because whatever the loads we have for AC loads, all the loads, all the electrical apparatus are designed for the 50 hertz. So this power, this PR power, the value of that is say 0.2 kilowatt. That power we cannot use directly. So what we have to do, we have to convert. If we want to use this power, then we have to convert this power from 10 hertz to 50 hertz, and that can be possible by using this arrangement. Okay, by using this power electronics converter circuit, we can convert this power from 10 hertz to 50 hertz. Okay, so and another thing is there, you just see this is the rotor part. So rotor part is, this is the rotating rotor, that means rotating part. Okay, and these power electronics converters are the static part. So directly we cannot connect that. Okay, we cannot connect these power electronics devices with the rotor circuit. Then what we have to do, we have to use the external means here. Okay, we have to use the external means here to connect the rotor of the rotating rotor winding or rotor circuit with the power electronics converters. Okay, so what are that external means or external device? The external device is lifting and brushes we can use here to connect the stationary part. This is the stationary part with the rotating part. Okay, now this is one advantage of DFIG over permanent magnet synchronous generator based wind turbine. What is that? That is the power electronics converter which are used in the DFIG based wind energy conversion system. Their ratings are only 20 to 30% of the fully loaded power electronics converters. Only why 20 to 30%? Because it is this rating of these power electronics converters are depend on the slips of the induction motors. Okay, so slip, if the slip is 0.2, so in percentage that is only 20%, and if the slip is your 0.3, that is only 30%. Okay, that's why the rating of this is very less as compared to this one. Okay, next is this DFIG. Okay, before that let me explain that. So what is the objective of these two converters? The objective of these two converters are, or let me consider this one first. So this converter circuit is called grid side converter. This is called rotor side converter. So why this is called rotor side converter? This is called rotor side converter because this is connecting with the rotor circuit. Okay, and this is called grid side converter because this converter, it is connecting with the grid, or if we connect this one with the load, then we can say this converter is load side converter. Okay, so what is the function of this, or what is the objective of using this grid side converter? The grid side converter, it is used to maintain the constant DC link voltage across this, like these converters. Okay, like these converters here also, this grid side converter is used to maintain the constant DC link voltage across this, so that we can get the power, variable power at a constant frequency, or you can say, so that we can get the power at the output of the grid set converter at 50 hertz. Okay, then only we can connect, otherwise it's not possible. So how we'll get that? That we can get if we can maintain constant DC link voltage across this, irrespective of the power variation. Okay, so this is very important part. And what is the function of this? The function of this rotor set converter is to achieve the variable speed. Okay, so that means what? By using this, we can inject the voltage in the rotor circuit. And we know that different methods are there to control the speed of the induction machine. So this is one simple methods. If we can inject the voltage into the rotor circuit, then we can control the speed. So whatever the speed we will get from here, from the wind, that is the variable. So we have to achieve the variable speed operations. So that variable speed operations we will get by controlling the rotor side converter. Okay, so this is called RSC. And this DFIG, it is operating in 3 different modes. So what are those? That just 1 minute, let me explain here, or let me write down here, then I'll explain. In 3 different modes we can operate this DFIG. So what are those modes? That number 1, super synchronous operational mode. Okay, the number 2, synchronous mode of operation, synchronous mode of operation, and number 3, subsynchronous mode of operation. Okay, so in these 3 mode we can operate this DFIG based wind energy conversion, subsynchronous mode of operation. Okay, so super synchronous, that means you just say, as this is your electrical machine, so then, or this is induction generator. So 2 speeds are there. One is called omega R, another is called omega S. Okay, so what is omega S? Omega is the angular synchronous speed. Okay, and this is angular rotor speed. Okay, so when we will get the subsynchronous operations? Subsynchronous operation we will get if the rotor speed is more than the synchronous speed. Okay, and synchronous, when we will get the synchronous mode of operation? Synchronous mode of operation we will get this omega R if both are same. Okay, then only we will get the synchronous mode of operation. And subsynchronous, that means if that omega R is less than omega S. Okay, so this DFIG based wind energy conversion system we can operate in 3 different modes. Now what are those modes? Number 1, super synchronous mode of operation, then subsynchronous mode of operation, and synchronous mode of operation. In super synchronous mode of operation, rotor frequency, or so we can say the rotor speed is more than the synchronous speed. Okay, so if we operate this system or this wind energy conversion system at this condition, then we can say this one working at super synchronous mode. Okay, and so in this super synchronous mode of operation, the power, direction of the power, because 2 powers are there. Okay, one is stator power and another is rotor power. So 2 powers are there. So if the system is working at super synchronous mode of operation, then active power, direction of the active power of the stator, or direction of the stator active power, it will be from stator to the grid. Okay, and the rotor's power, the direction of the rotor power also from rotor circuit or rotor winding to the load via the power electronics converters. Okay, so this will be the direction of the power during supersynchronous mode of operation. Okay, and for subsynchronous mode of operation, omega r, that means rotor speed, it will be less than the synchronous speed. Okay, so in that condition, the stator power, it will always flow from this side to this side. Okay, from stator to the grid. Okay, but under subsynchronous mode of operation, this rotor power, the direction of the rotor power, it will be from the grid to the rotor circuit. Okay, so this will be the direction of the rotor current during that subsynchronous mode of operation. Okay, and during synchronous mode of operations, no current, no power will flow from this side to this side and also from this side to this side, because it is synchronous mode of operation. So synchronous mode of operation, that means both the speed are same. That means the rotor speed and the synchronous speed both are same. So if both are same, then no current, no power, or no current will flow from this side to this side, and also no current will flow from this side to this side. So in that case, you just see, in order to get the synchronous model, or we know the for synchronous machine operations, we have to use the excitation system. Okay, without excitation, separate excitation systems, we will not be able to interlock the rotor magnetic field and the stator magnetic field. So we have to provide the external, or we have to use the external circuit. So using that external circuit, we can excite the electrical machines, and if using that excitation system or excitation circuit, we can operate the system at a constant frequency, or at a constant frequency, or you can say at a constant speed. So here, when this circuit, when both the speeds are same, that means omega r is equal to omega s, then the power will not flow from this side to this side and also from this side to this side. In that case, only this rotor side converter, it will act as a excitation system or excitation device, and this rotor side converter, it will inject the excitation signal into the rotor circuit of DFIG to get the synchronous mode of operations. Okay, so we have to remember that. So I will show you the diagram. Just 1 minute. Let's see. So here, this is the expression for the slip. Okay, so operating principle of DFIG. So that I already explained. Okay, so that rotor power is equal to S times of the stator powers, and operational modes of DFIG, that's subsynchronous mode of operation, supersynchronous mode of operation, and synchronous mode of operations. So subsynchronous mode of operation, this is subsynchronous mode of operation. Okay, so here you just see stator speed, this is the stator speed, and this is the rotor speed. Okay, so during subsynchronous operations, synchronous speed, it will be more than the rotor speed, and if the synchronous speed is more than the rotor speed, then rotor power, it will be injected into the rotor circuit. Okay, so the direction of the rotor power, it will be from the grid or from the load to the rotor circuit. So this is the directions. Okay, and the stator power, direction of the stator power, you just say it is from stator winding to the either grid or to the load. Okay, next is during the subsynchronous mode of operation, you just see stator power, it is also flowing from stator to the grid, and the rotor power, that rotor power, it will be fed to the grid via the power electronics converters. Okay, so here the direction of these two, this is the, or here the speed of the rotor winding, it will be more than the synchronous speed. Okay, and for the synchronous mode of operation, in the synchronous mode of operation, you just see this, the direction of the power flow, there will be no direction of the power flow, that means rotor power flow. Only this rotor side converter, it will use to inject the excitation signal into the rotor circuit to operate the induction generator at a constant speed. Okay, so how will get that operation? In order to get constant frequency operation, or in order to get synchronous, in order to operate the system at a synchronous speed, we have to provide the excitation signal into the rotor circuit. So this rotor set converter that will inject the excitation signal into the systems so that we can get the or so that we can operate this DFIG at a constant speed, and that the name of that constant speed is called synchronous speed. Okay, that's why this is called synchronous mode of operations. Okay, so here you just see it is written also rotor power PR is equal to 0. So there will be the no current will flow from the grid to the rotor, and also no current will flow from the rotor circuit to the grid. Okay, so this is the working principle of that. So here you just see it is mentioned here also. So during subsynchronous operation, the direction of the current rotor power, it is from this side to this side. Okay, and for the super synchronous mode of operation, direction of the current is from this side to this side. Okay, so that I already explained. That's why that DFIG is very popular nowadays. And DFIG, if we use the DFIG, you just see here. DFIG. So the most important part is to achieve the variable speed constant frequency operation. So how we will get the variable speed constant frequency operations? The variable speed constant frequency operations we can get by designing the control scheme or control strategy for the rotor side converter as well as for the grid side converters. Okay, so different type of the control strategies are available, like scalar control scheme and also the vector control scheme. Now, using vector control scheme, we can get the variable speed constant frequency operations. But if we use the scalar control scheme, then independent control is not possible. So independent control is not possible. That means if we want to operate only the voltage, that is not possible using the scalar control scheme. Or if you want to control the active power separately or reactive power separately, that is not possible using the scalar control scheme or scalar control strategy. So nowadays, vector control scheme is used, or vector control methods is used to achieve the variable speed constant frequency operation. And also, if we use the vector control methods, then we can control active and reactive power independently, and also the efficiency of the system, it is also increased. Okay, so if we use the variable speed wind energy conversion system, then we will get the better overall performances, and we will get the high efficiency, then possibility to control active and reactive power independently, then mechanical stresses and power fluctuations, it will be less, and also it provides 10 to 15% higher energy output as compared to the constant speed operation. Constant speed operation, that is also called fixed speed operation, that I already explained. Okay, so here you just say, now if we use the DFIG, so these are the advantages of the DFIG that we can use for the variable speed constant frequency operation. That means we can achieve the variable speed constant frequency operation. We will get the high energy conversion efficiency, then substantially reduction in the power electronics converter rating, that I already explained, because the power electronics converters are connected or they are handling only the slip power. Okay, that's why the rating is less. As the rating is less, then the cost of the system, cost of the power electronics converter, that will be less, and also the losses also, it will be less as compared to the permanent magnet synchronous generators. And also the decoupled control, that means that independent control of active and reactive power, that is also possible. Okay, so these are the advantages of DFIG based wind energy conversion system. So then how will achieve this, or how will get variable speed constant frequency operation? So variable speed constant frequency operations we can achieve by designing the control scheme for this rotor side converter, and also by designing the control scheme for the grid side converters. Okay, so as I already said, the vector control scheme is preferred to achieve the independent control of active and reactive powers, But if we use the scalar control, that is not possible. Okay. So if we want to design the control scheme for the rotor set converters, then the most important part is rotor position and rotor speed. Okay. What is the rotor speed and also the position of the rotor? Those two informations are very important part. So how we can achieve that, or how we can, or in order to get the rotor position information about the rotor position and also the informations about the rotor speed, we can use the sensor that is also called the encoder. So we can use the sensor or encoder to sense the rotor position and also rotor speed from the generators. Okay. So but if we use the sensor, to design the control scheme for the rotor side converter, then that control scheme or control strategy is called speed sensor control scheme. Okay. If we design the control scheme or control strategy by sensing the rotor informations, rotor position and rotor speed informations from the generator or from the DFIC, then we can say that control scheme is called speed sensor based vector control scheme. Speed sensor based vector control scheme. But in the speed sensor based vector control schemes are also have some drawbacks, or we can say the disadvantage. Like if we use the sensors, then maintenance is required. Then for the sensor, if we use sensor, then cable is required. Okay. Then cost of the system will increase. Then robustness, that means the less robust systems we will get, and also the cabling between sensors and controllers. Encoder failure, that means this is nothing but a sensors. Okay. So sensor failure is one of the most significant failures modes of these systems. Okay. So if we design the speed sensor based control scheme, then these are the disadvantages of speed sensor based vector control scheme. Okay. So nowadays this speed sensor based control scheme is not preferred. Why? Because of this disadvantage. Okay. So then how we can control that? How if we sense, or without sensing rotor position and rotor speed, if we can design the control scheme for the rotor set converter, then these problems, all the problems which are associated with the speed sensor control scheme, that can be overcome. So that's why nowadays the researchers, they are thinking to design speed sensor based vector control scheme. Okay. So why that speed sensor less vector control scheme is very popular? Because the speed sensor less vector control schemes overcome the drawbacks which are associated with the speed sensor based vector control scheme. Okay. That is very important part. Okay. So while your research will start, if you work on that, then you can think for that. That is one problem. Okay. Next is, now here, say this is the grid connected DFIG based wind energy conversion system. So in grid connected DFIG based wind energy conversion system, if any fault occurred over here, okay, so this is the fault, and let us consider that this is the voltage profile. Okay, this is the voltage profile. So throughout the operations, what we have to do, we have to maintain the constant DC voltage, constant voltage profile at PCC. Okay, at these bars we have to maintain the constant voltage throughout the operations. So if any fault occurs, say if fault occurred at this point, then due to that fault the voltage will decrease. Okay, so say this is the duration of the fault, and during this duration of the fault, voltage is decreased from 1 per unit voltage to, say this is 0.5. Okay, so if voltage decrease at this PCC, then we just see here two torques are there. One is this Tm, that is called the torque, which that is called the mechanical torque, and another torque which is developed inside the electrical machines, that is called the Te. So this Te, that means the torque which is developed inside the electrical machines, that is directly proportional to square of the voltage. Okay, square of the voltage, that means directly proportional to square of the stator voltage. So the stator terminals, you just see the stator terminal, it is connecting with the PCC. So the PCC voltage is decreased during this interval or during this fault. Okay, the PCC voltage is decreased. If the PCC voltage is decreased, then the electromagnetic torque which is produced inside the electrical machines, that is also reduced. Okay, so if this is the TM is reduced, but for a particular wind speed or wind velocity, this TM, that means this mechanical torque, that is always constant. Say if I consider the 12 meter per second, then this is constant, but due to this fault, the electromagnetic torque, that is decreasing. But for stable operations, these two, this is the dynamic equations, these two must be same, or you can say like that also. In steady state operations, TE minus TM is equal to 0. Okay, so now you just say for a particular wind velocity, this is fixed, but due to this fault, TE, that is decreasing. If this is decreasing, that means what? There we won't get this steady state equations. Okay, that means the steady state operations we will not get here. So in that case, there will be the mismatch between electromagnetic torque and the mechanical torque. And due to that mismatch between these two torque, the rotor of the DFIG, that will start accelerating. If the rotor of the DFIG start accelerating, then the rotor speed will increase, and that rotor speed, it may be more than the rated voltage, rated speed. Okay, if it is more than the rated speed, then the machine will damage, and also due to that accelerations, high current will produce inside the electrical machines. High current, that means high stator current as well as the high rotor current. So if for the high stator current, the insulation will damage, and that rotor current, you just see the power electronics converters, they are connecting with the rotor circuit. So that rotor current, it will tries to flow through the power electronics converters. So if the rotor current is more than the rated current, and if that more current or large current flow through the power electronics converter, then the power electronics converters also damage because their ratings are very less. Okay, so these are the difficulties if any fault occurred over here. So what we have to do in that case, we have to disconnect the entire system. If any fault occurred over here, then we have to disconnect the entire system, or we can say the wind energy conversion system from either from the grid or from the load. Okay, so here we have considered grid. So in order to protect the generators, in order to protect the mechanical components and also the power electronics converters, we need to disconnect the wind energy conversion system from the grid. But as per the national grid code, but because nowadays almost all the systems are interconnected power system, so suddenly we cannot disconnect that. Okay, so as per the new grid code, what we have to do, we cannot disconnect the wind energy conversion system suddenly. Okay, or immediately we cannot disconnect this one. So what we have to do, so we have to use the external circuit, or we have to use the external means or circuit, whatever. We have to use something here so that during the grid fault also, we can maintain the constant DC link voltage across this. Okay, so that can be done by using the FAX devices. We know that STATCOM, then SSSC, those devices we can use, and those devices will be active during the fault only. If the fault occur, only those devices will active, and those devices can't inject. If we use the STATCOM, then STATCOM, it will inject the reactive power into the systems, and if the STATCOM can inject the required amount of reactive power into the systems during the fault, then we will be able to maintain the constant DC link, constant voltage at PCC, not the DC link, constant voltage at PCC during the operations. Okay, so if we can maintain the constant voltage during the fault also at PCC, then I think then we no need to disconnect those things. Okay, so that is also one more issue. Okay, so we can think for that also. Okay, and another thing is there, if we connect the load here instead of this grid, if we connect the load, so load are, as we know, the load are nowadays maximum loads are non-linear loads. Okay, so if we connect the non-linear loads, then those nonlinear loads, it will inject the nonlinear currents into the systems. Okay, so due to the nonlinear loads, harmonics will be introduced into the systems. So if harmonics introduced into the systems, then we have to reduce the harmonics by the harmonics reduction methods. So there are different harmonics reduction methods are available, like your selective harmonic reduction methods, then third harmonics reduction methods. We can use the power electronic. We can use the FX devices also to reduce the harmonics. Okay, so different techniques are there. Even we can modify the control scheme for the rotor set converter, and also we can modify the control scheme for the grid set converter to minimize the harmonics. Okay, so that is also one challenging task. So we just see it is also written here. Okay, so the nonlinear loads nowadays are increasing. So the principal role of the wind energy conversion system is not only to capture the maximum power from the wind, but also to improve the power quality. Okay, so if the harmonics is or total harmonic distortion is more than 5%, as I already said, I think, then the quality of the power, it will degrade. So what we have to do, not only capture the maximum power from the wind, we have to improve the power factor also. Okay, so therefore it is necessary to use effective power quality improvement facilities for improving the power quality. So effective power quality improvement facilities, that means either we can modify the control strategy, or we can use the passive components that like capacitors, or we can install the active filters like your STATCOM, then SSAC, or you can say the FX devices. Those are called the active filters. So using active filters also you can improve the power quality. And there is a method that is called selective harmonic compensation method. So that selective harmonic compensation method also we can incorporate into the control system so that we can improve the power quality. Okay, so these are the different issues, and those issues can be overcome by modifying the control scheme or by incorporating the external device into the circuit or into the control strategies of power electronics converters. Okay, so and what is this? This is called the Crowbar protections. Okay, the Crowbar protection is used to protect the rotor circuit if any say if the rotor current is increased, or if the rotor current is increased due to any abnormal conditions, then immediately we can disconnect this part. Okay, in order to protect the this rotor set converter and also grid set converter. Okay, we have to disconnect this one, then use at the same time we have to active the Crowbar protection scheme. Okay, so if we active this Crowbar protection scheme, then the extra current that will flow through the Crowbar protection scheme. Okay, if it is flow through the Crowbar protection scheme or Crowbar protection device, then we will be able to limit the or reduce the rotor current. Okay. Next is, now what is the disadvantage of this one? Okay, so many advantages are available here in DFIG based wind energy conversion system, but it also having a disadvantage. What is the disadvantage? The number one is, you just see this stationary part. This is the stationary part. This stationary part is connecting with the rotating part. So how we can connect? We can connect this rotating part with the stationary by using the slip ring and brushes. Okay, so maintenance is required every 1 month or every 6 months. We have to replace the slip ring, and also we have to replace the brushes. Okay, so this is the main disadvantage of DFIG based wind energy conversion system. Now, if the DFIG based wind energy conversion system is connected with the interconnected system, so that is a very challenging task. That means we have to shut down this, then we have to replace that slip ring and brushes. Okay, so this is the main disadvantage of DFIG based wind energy conversion system, and this disadvantage can be overcome by using another wind turbine generators. Okay, so this is another wind turbine generators here also. Okay, you just say this is also wind turbine generators. Now this wind turbine generator is called BDFIG. So what is BDFIG? BDFIG, that means brushless double fed induction generator. So brushless double fed, that means here you just say brush and the slip rings are not required. Okay, brush and slip rings are not used here. Here also brush and slip rings are not used. Okay, that's why these two generators are called brushless. This is called brushless double fed induction generator, and this is called brushless double fed reluctant generators. Okay, why it is called reluctance? Because this rotor is designed using the iron. Okay, so that's why the name of this rotor is called reluctance rotor. Okay, that's why the name of this generator is called brushless double fed reluctant generator. The double fed, that means you just two output. Power can flow from this side to this side, and also power can flow from the stator windings. Okay, so that's why that is called double fed. And brushes are not there. That's why this is called brushless. Okay, so B implies brushless. So here in this is the rotor part. Okay, so this rotor part is this one. So rotor is not connected with the power electronics converter. So here you will see the power electronics converters are connected with the rotor. But here the three-phase windings or three-phase stator windings and the three-phase rotor windings are not connected with the rotor part. Similarly, here also you just see rotor is not connected with any power electronics converter, and it is also not connected with the grid. Okay, so in these two wind turbine generators, actually two stators are there. That is very important. I think till today you have heard that in the electrical machines only one stator and one rotor are available. But nowadays there are those three-phase electrical machines are designed without the brush or without the slip rings. Then for those generators or for those electrical machines, two stators are there. Okay, so this is, you just see, this is stator number one. This is the stator number one. This is stator number two. Okay, so two stators are there and one rotor is there. Similarly, here also two stators and one rotor. Okay, so what is the difference between these two? The difference between these two, here the rotor is own rotor type. Okay, and here the rotor is reluctant rotor. Okay, or we can say the as non-salient type rotor. Okay, then how we can control that? That because we have to use the power electronics converters. Then without power electronics converters, we cannot control the frequency. We will not be able to get the variable speed constant frequency operations. That means we have to incorporate the power electronics converter. So here you just see this is the power electronics converter. Now this power electronics converter, it is connecting with one of the stator and the grid. Okay, so out of these two stators, this stator is called primary stators. This is called the secondary stators. Okay, so the primary stator, it is connecting with the grid, and the secondary stator, it is connecting with the grid via the power electronics converters. Okay, so what is the difference between these two? Both are stators. The difference between these two is pole number for primary stators and the pole number for the secondary stators are different. Okay, so for pole number one, you say the pole number of pole is P1, and for secondary circuit or secondary stator winding, pole number is P2. Okay, so these two poles are different. Then which one is more? The P1 number of pole for primary winding or primary stator winding is more than the number of pole for secondary stator windings. Okay, so this is the conditions. Okay, so what is the difference between these two? The difference between these two is their pole numbers are different. Okay, so then how it is working? This is actually working based on the modulation scheme which are used in the electronics people. In the electronics people, they are having the communication subject. In the communication subject, they are using the modulation. Okay, so the same modulation technique is used here also. That means these two wind turbine generator, these two generators are working based on the modulation concept. Okay. So that only that is. So these are the advantage and disadvantage of different type of the wind turbine generators. Okay, so all the things are written here. You please go through. I will share on these things. So what is the use of power electronics converters? The power electronics converters are used to control the frequency. Then, as I already explained, then magnitude of the output voltage, output voltage, then output power. Output power, it may be active and reactive power, as well as the steady state and dynamic behavior of the systems. Okay, so power electronics, using power electronics converters, we can do many tasks. Okay, like we can control frequency, we can control the magnitude of the output voltage, then we can control the active and reactive power, we can control the speed, we can control the torque. Okay, many things we can do. Okay, and also we can study the steady state and dynamic behavior of the systems. Then as the amount of the installed variable speed wind turbine system increased, so has the importance of the power electronics converters in wind energy conversion systems, since it is the interface between the wind turbine generators and the electrical grid that I already explained. Okay, so within this power electronics converter can control that is also explained. So in variable speed, constant frequency of the reference electrical sequence is locked. Okay, that is the synchronous bit. Okay, so you just see now the classification of power electronics converters which are used in wind energy conversion system. So these three type of power electronics converters are used to design the wind energy conversion system. So this is called the back-to-back converters. Okay, the back-to-back converter that I already explained, just now I have explained here. This is called back-to-back converters. Okay, so this is called back-to-back converter, and in back-to-back converter, total 12 switches are required. We just see here 6, and here also 6. Then total 6 switches are required. Then we can use the matrix converter. So this is the matrix converters. So here total 9 switches are required. Okay, so as the number of switches are decreasing here as compared to this one, then the switching losses will be less. Okay, switching losses will be less, and also the cost of the systems will also less as compared to this one. Okay, then multi-level converters. So different, this you just see here how many levels, 1, 2, 3, 4 levels are there. Here also 4 levels are there. So multi-level converters also we can use. Okay, but these matrix converters, this one we can use only for unity power factor operations. I repeat, this, what is the disadvantage of this one? The disadvantage of matrix converter is that it can used only at unity power factor operation. Only at unity power factor operation. That means we cannot use this matrix converter, or we cannot operate this matrix converter at say 0.5 lagging power factor or 0.5 leading power factor. For other power factor, we cannot use that matrix converter. So many research are still going on these matrix converters, so that that means so many modifications are still going on. Okay, so that we can operate this matrix converter in all type of the power factors. Okay, so these are the advantage and disadvantage of these three type of the power electronics converters. So please go through that. Next is different modes of power wind energy operations. So wind energy conversion systems we can operate either in isolated mode, and also we can operate in interconnected mode. Okay, so isolated mode, that means that wind turbine system or wind turbine conversion systems, it will not be connected with the grid. Okay, and the wind turbine, it may be one wind turbine, maybe there or more than one also. Okay, so one or more wind turbine not connected grid. Okay, so isolated system, that means that is standalone system that will not be connected with the grid. Okay, simply whatever the energy will convert from the wind to the wind energy into electrical energy, that entire energy it will be fed to the grid, or it will be fed to the load. Okay, so in this type of system is called the standalone system, or isolated mode wind energy conversion system. Okay, so here you just see, and these type of operations actually are used in interior area where the main grids are not available, but the wind speeds are available. So for those locations, we can install standalone based or the isolated mode of wind energy conversion system. Okay, so in isolated mode of operations, the most important part is we have to use the extra device here. Okay, so that extra device, the name of that extra device is called storage unit. Okay, so we have to use this one. Why we have to use this one? Because say the wind energy, the wind from the wind, say we are getting 1 kilowatt power. Okay, and the load is your 500 watt. Okay, so the total generation is 1 kilowatt, but our demand is only 500 watt. Then where that extra power will go? That extra power, it will be stored in the storage unit. Okay, out of this 1 kilowatt power, 500 watt that will fed to the load, and extra 500 watt that will be fed to the, or that will be stored in the storage unit. Okay, then after that, then say the generation, it becomes 200 watt. Okay, and the load is 500 watt. So the load is more than the generations. As the load is more than the generation, then that extra power, that means what? Here we have to, this 200 watt, it will flow from this side to this side. Okay, then the demand is more than this, that means 300 watt extra power are required to fulfill the demand. Then from where we will get this extra power? That extra power we will get from the storage unit. Okay, this storage unit, it will supply the extra 300 watt power to the load to fulfill the customer demand or to fulfill the load demand. Okay, so here the most important part is we have to use the storage unit. That means either battery or supercapacitor. Those things we can use in order to design the standalone based wind energy conversion system or the isolated mode based wind energy conversion system. And in the interconnected mode of operations, you just see wind turbines, it will be connected with the grid. So here you just see it is connected with the, this is not the compulsory part. Okay, this is not required. Okay, but it may be there also. Okay, but this is not required. Whatever the power will be generated here, that entire power we can feed to the grid. Okay, or we can store in here if required. Then we can store here also. Okay, so this is compulsory. Storage unit is compulsory for the standalone system or isolated mode of operations, but for interconnected mode of operations, this is not compulsory, but we can connect that. Okay. So this part I will explain in next class. The details of standalone wind energy conversion system, and also that I already explained this voltage stability problems, the grid. This part I already explained. Okay, so this part is already completed. And this one I will explain next week. Next week, I don't know. Next week. So this is finished. This is also finished. And next class, I will explain only the standalone wind energy conversion system. This is, then I will start that mathematical modeling. Okay, so mathematical modeling, then the control scheme. So that all the things I will explain. Okay, this is the very important part. So that I will explain next class. Now, if you have any doubt, you can ask me. And in the meantime, let me take the attendance. Can you hear me?
Yes, sir.
Okay, I have taken attendance. Now, if you want to ask question, you can. Otherwise, you can leave.
Okay, thank you, sir.
Welcome. Welcome.